So at SandLab, my lab at MIT, the Stochastic Analysis and Nonlinear Dynamics lab, we try to address two key challenges related to the prediction, the quantification, and the mitigation of extreme events. The first one is related to the fact that extreme events are rare, so you don't have all the data you would have in other situations to train, let's say, a machine learning model. The way we try to address this challenge is by taking advantage of all the available conservation laws, governing equations that are typically available for both engineering systems as well as systems that one finds in the environment. And the second key challenge is associated with the complex dynamics that governs extreme events, in particular nonlinear, chaotic dynamics. Chaos makes the whole problem much more challenging because, let's say, for example, you have some ground truth data, the evolution of climate over the last 10-20 years, and then on the other hand you have an imperfect model. So how do you improve your imperfect model when you cannot really match the two things simply because they diverge due to their very nature, right? Due to chaotic dynamics. So this is one of the key or one of the most fundamental challenges that prevents the direct application of otherwise successful machine learning algorithms in problems of this type, and we spend a lot of time and effort on trying to formulate algorithms on the intersection of dynamical systems, probability, and machine learning to address exactly this type of challenges. Related to the problem of rarity of extreme events, one of the techniques we're using is to design optimal experiments. This can be either numerical experiments or physical experiments. So for problems that you have the luxury of doing that, because it's not all problems that you can design an experiment and run it with the parameters that you want, but for those problems that we can do that, we are trying to identify the experiments that are the most informative when it comes to extreme events. Let's take, for example, a problem with the ship that is subjected to random waves. The brute force approach would be to run a numerical or physical experiment where you just generate random waves for a very, very long time and then try to analyze the statistics of the obtained time series, right? That, of course, will take an enormous amount of time because the extreme event will not appear immediately, it will appear, after a very long time. What we are trying to do is to, in this case, is to parameterize all the possible random waves through some type of mathematical construction, and then carefully choose the parameters of the wave so that we can explore events that are not just extreme but also feasible, because you don't want to spend all your computational or experimental resources understanding waves that will never occur, but on the other hand you don't want to focus on the events that are going to be boring and will not generate any interesting outcomes. So this sort of exploration, of very careful exploration in regions of the parameter space that are both interesting and in terms of generating extreme events but also feasible, this is one of the key innovations that we have been able to achieve, and that allows us to be able to capture the statistics of extreme events with orders of magnitude lower computational costs.